Meeting is being recorded.
Hello. Today we're going to talk about seeing and understanding networks. This is a project where our goal is to see and understand data that involves relationships between things. And I want to caution you that this is research. What we'll be showing isn't anything that's shipping right now, it's things that we're looking into. So Tableau is really good at helping you see and understand data that's stored in tables, which I suppose shouldn't be too surprising given our name. Our early CEO, Christian Chabot, used to tell a story of the first time he tried to sell Tableau to a French company. And they just looked at him with a confused expression saying, "So you named your company Table?" And yes, we did, for a really good reason. Tables are a simple but really powerful way to model information, which is why there's so many relational databases. In a well-shaped table, every row represents the same type of thing. And every column represents a property of the thing. So a row might be people, or sales, or a flight. Column could be a name, or a dollar amount, total sales or cost, or a distance. And using that simple model, we get all of the visualizations that Tableau supports. So here we have hurricanes off the east coast of the US. Every line represents a different hurricane. The color and thickness represents how intense the storm was. And this all comes from a table. Every row in the table translates to a mark in the visualization. Every row is a wind reading, therefore every mark represents a wind reading. Then you take the columns and turn those into visual encodings. So you have the latitude and longitude determining position, you have the category and destructive force determining the color and size of the mark. Once you want to work with multiple types of things, then you use a dashboard. So here we have the year in one visualization. Every mark is a year and has properties like the number of hurricanes in that year. Here we have every mark being a hurricane with properties like name and year and maximum wind speed. Here's the visualization we saw earlier. And here's another view of that same table where we have properties like the date and the maximum wind speed, so we can see when the storms occurred and how intense they were. You put those all together into a dashboard, tie them together with filter actions. You click on 2005, it filters the other visualizations to just that year. Then you click on the different storms, and you can bring up just those storms that'll filter the other visualizations. And this model supports a lot of common domains, but it doesn't support everything. For example, let's say that you had an org chart for a company and you wanted to understand whether it was a really shallow organization or very hierarchical, and so you might ask questions like, what's the longest management chain? Here it's 5 to go from the CEO to it's 5 or less to go from the CEO to anybody in the org. Or maybe you want to know what's the total org size of Jane, all her direct reports and their reports and their reports and so on. In this case, it's 11. Or here I have a map of the Nordic countries. All the dots are different towns. The lines are train routes, and the numbers on those lines are how much it costs to take that train. And you might have a natural question of, well, what's the least expensive route between two places? For example, if you want to go from Bergen on the west coast of Norway to Helsinki, Finland, you can see that there are a lot of different routes you could take that all have different total prices. If you've ever played the game Ticket to Ride, you recognize this as a network game. It's all about choosing routes between different cities. So you draw multiple route cards, and maybe a route card takes you from Bergen to Helsinki, and you need to place your trains to connect those two cities. But it's a little more complex than that because you actually have multiple route cards. It might be better to do a less direct route so that it can connect multiple routes at once. And then, of course, you're playing against other people that are also placing trains, and they might have blocked you, and so you need to take a different route around there. Another question that's pretty common, and you would expect Tableau could help you with, is given that a customer bought X, what else did they buy? The reason that this is a little more complex, it's a little bit outside of what Tableau can do, is because it involves multiple connections between things. So you start out by looking at a particular product, like longer life soft white bulbs. And you need to go from product to all the customers that bought that product. And from there, all the products that those customers bought. And then you really need to roll up all those products onto that top level product, maybe deduplicate them because you can see multiple customers bought the Newell 318. And so it's these multiple connections between things and rolling up data that across those connections that Tableau can't help you with right now. So before I continue on, I want to give you a little bit of terminology that we'll use in the rest of the talk. So those boxes represent things like products and people. Those are called nodes. The lines between things, those connections, relationships, are called links. Both nodes and links can have properties like the name or price or whether it was a bought by relationship. And then that whole diagram together is known as a network or a graph. So let's go back to that question. Given that a customer bought X, what else did they buy? And I'm going to answer this using a research prototype that I've been working on. And again, I want to warn you, this is research. This is not something that is shipping. So we'll go over to the prototype, and we will grab some customer data, drag that in. Now this data, you might recognize it's one of the sample sets that ships with Tableau. This is a table. Every row in the table represents a line item in an order, and each of those columns represent different properties of that order. So things like the customer who purchased it, how much it cost, the information about the order, date and ID, the product that was purchased, how much it cost, all that. Up top here, I have data models that you can create. And the one data model I have right now is that table that you see. But I want to create a new data model. I'm going to create a graph. And we're going to look at the different properties of those graphs. All of these buttons represent different categories of things you can do to build up this graph data model. The first thing I want to do is create a node for every product. So what I can do is pick up product, drag it over to nodes, and when I drop, it has created a node for every product. So when we look at the table itself, you can see there are almost 10,000 line items in different types of orders. And when I pull out all the products, you can see there's 1,850 different products in here. Now we want to create nodes for all the customers. So in similar vein, I can pick up customer, drag it over to nodes, and I can see that there are almost 800 different customers. If I want, I can drag other properties onto those nodes so I can see what the profit is per product name. So in that case, I think I will just leave it as product. So now what we want to do is, given that they purchased a product, I want to find all the customers who purchased that product. So I can pick up product, drag it over to customer. This creates a new type of link that takes me from product to the customers who bought the product. So here I can see, given a bookcase, Claire, Arthur, Seth, and Herbert all bought that bookcase. Now what I want to do is, now that I've got those customers, I want to find for each customer what products did they buy. I want to go the other direction. So given a customer, what did they buy? So I drag it the opposite direction. It creates a new set of links. And then when I look at the graph that I've just created, again, I can see here's the bookcase, here's Claire, Arthur, Seth, and Herbert, but I can also drill into each of those customers to see what they bought. This is now getting me close. I can now go from a product that was purchased to the customers who bought it to the products that they bought. But my question didn't involve individual customers. It involved aggregate behavior. What are all the other products that were purchased with that original product? So what I really want is all these nested products down here. I want to pick those all up, drag them up to the top level. When I drop that, now you can see that I have all the information all collected together. So given that someone bought a bookcase, here are all the other products that were purchased with that bookcase. So at this point, I now have enough information that I can answer my original question. And so with this prototype, I could continue to drill in, explore different products, what was purchased with it. Or if I wanted to bring this into Tableau, what I could do is turn this graph back into a table, or specifically the information that I had just collected out of the graph. So what I want to do is take all those products and then drag them up to data model, and it creates a new table for me that has exactly that information that I was interested in. Bookcase to all the products bought with it, so on for other products. But this isn't quite the form that I want to work with in Tableau, because Tableau isn't as good at working with a table cell that's a list. So I really want to take this column that has lists in it and create a row for every item in that list. So when I drag product up there, it now has pivoted the table a bit. So now I've got a line item for every product to product that was bought with it. And now I could bring that into Tableau and do further analysis with it. I'm going to do a second example that is European royalty over many centuries across all of Europe. So as you might imagine, this is a very tangled, interesting data set. This raw data came from a family tree program, and so it has records for individuals, like here's Queen Victoria of England, and underneath it are nodes for where she was born and died and married. There are also IDs in here that reference other records elsewhere in this data. So you can see $ID with the @ signs, that's her ID as an individual. You also see at the bottom of her properties, @F1 and the other family ID. Those point to family records, where Fam S is the family she's a spouse in. Fam C is the family she's a child in. And so what I want to do is create links based on those IDs to the other records. So rather than go through all the steps to do that, I'll just drop in the finished version of that. Once I can grab it. And now you can see here's Queen Victoria. Here's the family she was a spouse in. She was married to Prince Albert. King Edward was one of her children. Here's the family that she was a spouse in. Apparently she was an only child. So now I can go step between individuals and families and go explore this web of family relationships. But sometimes stepping between nodes and following links isn't exactly the way I want to explore this data. I would like to just look at Queen Victoria and see information about her spouse and her children without having to step through multiple links. And I have this graph, this network now, with all that information in it. What I want to do is move information across those links to get them in a more convenient location. So I can do that with the help of a few more transformations in my graph data model. And now I have on the Queen of Victoria record, there's her husband, there's her children, I can still go and explore the relationships in there, or I can just get the information right on the nodes. Okay, if you were paying close attention to that research prototype, you might have noticed the name of it. And I want to give you a little bit of background on where that name came from. First off is Polaris. For people who've been following Tableau for a while, you might know Polaris as a research project that two of Tableau's founders, Chris Stolte and Pat Hanrahan, worked on, that was a formalism for turning tables into visualizations. Polaris became BizQL, which is the foundation of Tableau. This is the secret sauce of Tableau. You may also know Polaris as the North Star. The name of my research prototype is Ursa Minor. If you're familiar with astronomy, constellations, you might know that as the constellation, the Little Dipper, or literally the Little Bear. And that star right there is Polaris. So the name of the research prototype is Ursa Minor because Polaris is just a point in a graph. And as I've worked on this graph of being able to see and understand networks, I've run into a series of interesting challenges, some contrasts with Tableau. One of the challenges is that data doesn't start out as a nicely shaped network. A lot of times it starts as a table or JSON or XML. It starts in some form that isn't the network that will help me answer the questions. So a lot of times answering the question involves figuring out what that network should look like, how it should be shaped. So part of the analytic flow of answering network questions really needs to support creating and modifying the network itself. Second challenge is that networks often consist of very heterogeneous things. So if you recall, the way that I described a table is that every row in that table represents a single thing. Whereas in some of the networks that I've shown you, there have been multiple kinds of things. Maybe it's products and customers or people and families. But there are other times where the network can actually be a whole bunch of different types of things. Some of you may have tried cracking open the Tableau workbook format and looked inside there. And what you would find is basically a network, a simple hierarchy, a tree, with hundreds of different types of nodes in there, hundreds of different types of things. And inside the workbook, there are data sources with fields and map sources and actions and worksheets with all sorts of different nodes under them and dashboards and so on and so forth. And so there are other links in there as well. So dashboards can reference worksheets, which can reference fields, actions can reference any of those things. And so you've got the hierarchy implicit in the workbook format itself, but then you've got lots of cross-references that create new links. And each of those types of links can be different things as well. So unlike Tableau, which has a simple model because when you're building a visualization, you're only working with one kind of thing at a time. But with networks, you could be working with a whole bunch of different things all at once. So you really need a powerful way to be able to treat different nodes and links differently for selection, for encoding, so on. A third type of challenge is that if you try to display an entire network, even a relatively simple network, you often end up with something that looks like this. In the visualization and network community, we affectionately refer to this as the hairball. This hairball really only answers one question. Is it complex? Well, yes, because it's just a hairball. But you can't really get much more insight out of that. So you have the challenge of finding the data that you're interested in, and displaying the entire hairball just isn't a useful way to start. So you need to be able to search. And a common approach for searching is pattern matching on the structure of the network and properties of the nodes and links in the network. Okay, so what I've talked about so far is going from raw data and turning that into a useful network for doing further analysis on. But I haven't talked about effective ways to actually display that network. So to talk about that is my colleague Matt Bremer, and so he will take over from me. Yeah.
Thanks, Scott. So as Scott mentioned, with his prototype, we can now construct relationships with the data that we have. So in this part of the talk, I'm going to talk about effective strategies for visualizing and interacting with these networks. So I'm also a research scientist with Tableau Research, and part of my work is focusing on data visualization and keeping tabs on what the trends are in the wider visualization community, both in the research community and among practitioners. So I'm going to show you a few examples of network visualization that I find compelling, and hopefully you will as well. All the examples that I will show were not produced using Tableau, but nevertheless, they do inspire us in some of the ways that we're thinking about visualizing networks in the future. Now, when I say visualizing networks, perhaps some of you will imagine something that looks a bit like this. This is a node link diagram where we have circular marks connected by link lines. This is a fairly common representation, and the nodes and links here are arranged. You don't have to arrange them manually yourself. What often happens in cases like this is the topology or shape of the network is laid out using what is often referred to as a force-directed layout algorithm, which attempts to minimize visual clutter and the extent to which these link lines overlap one another. Of course, it's not perfect. You still have a lot of overlapping lines, but you can see some of the structure of the network here. You have that fan-out structure toward the left, and you have that nice interconnected cluster of links and nodes at the top and at the bottom. However, even this doesn't scale to very large networks. This is a fairly small network, but once you get a little bit larger than this, node link diagrams created with a force-directed layout often devolve into the hairball problem that Scott was just mentioning. So really all you can grok from this is that you have something complex and highly interconnected. Interacting with something like this can be really frustrating. So let's look at some alternatives from the broader visualization community. And I'll be referencing work by researchers, practitioners, and designers who have found ways to effectively visualize networks. The first example I want to show is one that separates and arranges nodes categorically. So as Scott mentioned, often a network contains very heterogeneous things, and you want to lay out the things that are different in different spaces. So what you see here is a visualization by the designer Christian Lesser, and it's a visualization of a podcast. In this case, it's specifically the Data Stories podcast, and the Data Stories podcast is about data visualization. So if you're interested in hearing different takes on the world of visualization, I highly recommend checking out that podcast. But what happened after they released the 100th episode of the podcast a couple of years ago was they released their data set of all of the guests and all of the topics that have ever appeared on this podcast. And this is what the designer Christian Lesser took to build this network visualization. What you have here is a set of nodes arranged in concentric rings. All of the podcast guests or the interviewees on the different episodes of the podcast are around the outer ring of this visualization. And then each of those nodes, these people around that outer ring, they're sized according to how many appearances they had on the podcast, and they're colored according to their gender. In the next most ring, in the middle, we have all of the podcast episodes themselves, and they're arranged in chronological order, and they're sized by their duration in minutes. And then finally, in the middle of this network visualization, you have all of the topics that are discussed in this podcast. You have them laid out and indicated by the meta level topic, and that's just a text label. And you have all the subtopics connected around those. Now, in addition to distinguishing different types of nodes and arranging them in different locations, the designer here has also assigned a way to interact with this network and see those interconnections, to surface those as you hover over the different parts of this visualization. So in this way, this example is a bit like Scott's product example, but instead of asking questions about which products do people tend to buy together, this is a case where, given this topic on this podcast, what other topics do people talk about in the world of data visualization? All right, time for another example. So another example that Scott mentioned had to do with the relationships between European royal families. And as Scott mentioned, these families are highly interrelated. So if you attempt to draw these relationships using a default topology-based layout or a force-directed layout, you'll likely get a hairball like you saw earlier. So in this case, this is work by the visualization designer Nadia Bremer. It's a work called Royal Constellations. And it takes that European royalty data set and solves the hairball problem by arranging the network in an invisible grid. What you have here along the vertical axis is the date by which people were born, with most recent at the top and the oldest births toward the bottom. Along the horizontal, you have all the different royal families corresponding to different countries in Europe. The big bright nodes are the current royal monarchs from the different royal houses. She's also diminished the opacity of the links between people in this network so that more recent connections are more salient. You'll see that these link lines toward the top are a little bit more salient than the ones toward the bottom, that they diminish further and further into the past. Another interesting thing that she's done here is when you hover over nodes, you can see who's connected to that local network around that person. And she's also allowed you to select 2 nodes in this network to see how people are related. And then you can browse along that path to see who is connected and what is that chain of connections that link one person to another in this network. Now, another solution to the hairball problem is to only show the links on demand. And this is especially helpful when you have a lot of interconnected links and nodes that are really close together. So this example, this is work by the researcher and designer Marianne Dirk. And each node that you see here is a single Western philosopher, and they are positioned according to how similar they were to one another in terms of their bodies of work. And here the designer has chosen to only surface these relationships when you interact with this network. So as you see here, when you hover over any of these nodes, you see who it is. But then when you click to select any of these, you then see the patterns of influence of one philosopher on another's work. You'll also notice that these links between people here in this network are directed. You're seeing who influenced who. And that's indicated by the directionality of these connections. Were you to show all of these connections all at once, of course you get a hairball, but then you'd also have a hard time distinguishing who influenced who, especially in cases where philosophers were contemporaries and they may have influenced each other during the course of their lives. Up until now, a lot of the examples that I've shown assume that you have control over where you place the nodes in your network. But what if the nodes in your network have some meaning already? What if they have specifically a spatial position? If your nodes in the network correspond to an address or a city, perhaps. Earlier, Scott mentioned the example of rail connections across Scandinavia. I'm going to show you a slightly different example, but perhaps with a different geography, that of airports in the continental US. Now, if you were to simply draw all these links as straight lines between all these airports, it could lead to what you see here. It's kind of a messy hairball, a tangled web of connections between airports, and it's hard to discern how these nodes are connected to one another. One way to resolve this problem of all these links in a geographic network is to consolidate common connections. And this is what the researchers Danny Holton and Jack van Wyk came up with over a decade ago, this concept of link bundling. And it consolidates all these common connections between nodes to visually distinguish this degree of consolidation, and done so with color and with gradations of line thickness and opacity. So what you have here on the right is something more akin to, say, an interstate map rather than a map of connections between all roads. So doing this, this link bundling makes it a lot easier to see the structure of the network and to follow some of these consolidated connections between busy parts of the network, which you see here in the northeast of the US, and connections down to hubs like the Los Angeles area. You can take this link bundling further by emphasizing emphasizing the directionality of connections between nodes. What you see here is a selection or a sampling of different techniques that researchers have come up with over the years for bundling links together to clean up a network diagram. The approach that I want to highlight here is a relatively recent one called Confluent drawing. And this is this last one in the bottom right. This approach takes inspiration from the confluence of rivers and how connections flow from source to destination. Here, the curvatures of the links, in addition to the inclusion of arrowheads on the ends of the links, really visually reinforce the directionality of the connections between nodes in the network. And this is just one possible strategy for you to communicate how those connections connect to one another and the directions between them. Another strategy for emphasizing the directionality of relationships in a network is to use animated links. In this example here, the designers Hugo Rama and colleagues proposed this technique for animating the connections between nodes in a geospatial network. What they've also done is reduce the opacity of the middle parts of these connections to really visually emphasize the sources and destinations of these flows in the network. Draw your attention to those origins and destinations. Now, everything I've shown you until now is also assumed that your network doesn't change over time. But as we know, networks often do. For example, if you consider, say, a social network, people enter the network, people leave the network, people might form new groups, or groups might dissolve or reappear. So not only might you end up with a hairball, you might end up with a moving hairball that changes over time, and we want to avoid that. So what are some strategies that people have come up with in the broader research community to resolve this problem? Once again, you can leverage things like interaction and selective highlighting to emphasize how a network changes over time. So in this example, this is work by Benjamin Bach and colleagues. This is a project called Graph Diaries from a few years ago, which shows how a network changes over time. As you see in the main view, you see this network animating, and you see the parts of the network that are either entering or leaving the network being visually highlighted. And you also see along the scrubber, along the bottom, where things are changing in the network over time. And you also have a set of thumbnails that show different time slices of that network and its structural change. So by now you might have also picked up on another recurring theme throughout my examples. All of the examples I have shown so far have been variants of that node link diagram, or circles connected by lines. But it turns out that there are other ways to show a network beyond circular links, circular nodes and link lines. Some of you may recall printed road atlases. And if you flip through one of these, maybe at the front page, the back page, you might come to a mileage chart. You have destinations and origins arranged in a grid. If you want to find out how to get from New Orleans to Mobile, you would look up the row of New Orleans, and then you would look up your destination along the column, and where those points meet in the grid, that'll tell you your mileage. Turns out that you can do a similar thing with networks of nodes and links. That's what I show here. What you can do is you can list all of your nodes in your network as rows and also as columns. And here you can color your cells according to the type of connection between them. And you'll also notice that there's a lot of empty cells here. And unlike a mileage chart, this is where they differ. You may have connections that don't exist between pairs of nodes, and that's represented here by empty space. When you do have a connection, you can color in that cell in the grid, and that'll tell you whether a connection exists between two nodes and the type of connection, in this case represented by color. You may also have directionality in your grid. In this case, your grid will not be symmetric, and this, what we're seeing here is a totally symmetric network, which means that for every connection between two nodes, that connection is bidirectional. So there's a lot of redundant information in the upper diagonal of that grid. You don't often need that upper diagonal if your network is symmetric. If you had directional links in your network, that would not be a mirror image along the diagonal, and you'd still want to retain that upper half. Now, one advantage of this representation is that you'll never have link crossings. You'll never have the hairball problem, since everything is just a table with no crossings of any lines. I also want to step through how you would transform a node link representation into a grid representation so you can see that correspondence happen. I'll also mention that the technical term for that grid representation that you see on the right is known as an adjacency matrix. What I've done here is I'll highlight the same node in these two representations. I'm going to point you to this yellow node that's connected by a blue link line to a pink node. And you can see that how it's connected in both representations. How you transform that node link representation into the grid is you start by, in this case, twinning all of the nodes, all of the links between nodes. This is because, in this case, there's no distinction between the directions of these links, and you have a symmetric grid at the end. If you did have directions in this case, you would not necessarily twin these links. And then the next step is to reposition all of these nodes along a diagonal. And you transform the arcs into rectilinear connections that follow a grid layout between these nodes. Now the result is that every node has a row and every node has a column, and that each grid cell you color according to whether there's a connection between those nodes. So with this grid representation, patterns of connectivity and clusters like the one you see in the bottom right of the grid representation, they become much more apparent. And you, as I mentioned earlier, you do not have the case of link crossings. You can take this grid representation even further with introducing another metaphor, the subway map, which allows you to show patterns over time, how a network changes. In this case, we're looking at patterns of collaboration between people over the course of 4 years, and each person in this network gets their own subway line. And in this case, their colors might represent where they might be geographically, or maybe their affiliation if this is collaborations between people that are in different organizations or in different teams. So each person has also a pair of initials. And if we look at just that first year in 2008, we have 5 people. And you, in addition to seeing people along the horizontal, the subway lines, you also have the people are repeated along the horizontal. And in each year, you have that grid representation. And if you look up within each year whether a person has collaborated with another person, you would color in a subway stop on their line. And then you would repeat the same thing for subsequent years to see how the network changes over time. Maybe new people enter the network, which is indicated by a new subway line appearing. And you can see the patterns of collaboration maybe differ from year to year. Maybe someone also leaves the network, such as in 2011 when FC leaves, and perhaps they reappear later in the network. So to wrap up, I just gave you a whirlwind sampling of what people in the broader visualization community have done to better see and understand relationships in networks, and also how to interact with these representations once they've visualized them. I've sampled from the space of visualization research, as well as work by visualization practitioners and designers. As I mentioned earlier, none of these examples were produced using Tableau, but they're nevertheless strategies that and techniques that continue to inspire us in our research when it comes to thinking about how we might offer network visualization support in our future products and research prototypes. So if you're interested in hearing more about this research that we're doing, please visit our website at research.tableau.com, where you can learn about not only our visualization research, but all the other research projects that we are engaged in at Tableau Research. So with that, thank you very much for your attention, and I'll turn it over to the audience for questions. Thanks.